This question is probably the easiest calculation we do this semester, but it's also very important for understanding what conditions are like on a planet's surface. This time, we're calculating a planet's surface temperature based on the light it emits. Remember that the name for the light emitted by an object because of its temperature is thermal radiation. So we're using thermal radiation to measure the temperatures of planets. There's not a lot of data the question needs to give us, so we can move right on to the prediction. You're asked to predict which outer planet has the hottest surface and which one is coldest. There are a couple of ways we can do the prediction. The first one is based on simple experience. Can you look at where these planets are in the solar system and decide which one you expect to be hottest and which you expect to be coldest based on location? The other approach is to look at the column that lists the wavelengths of light emitted by the planets. Remember that wavelength isn't a measure of how much light the planet produces. Instead, it's a way of describing the color of the light the planet glows in, although it's really a color in the very broad sense of the word, since in fact these wavelengths are all infrared rather than visible light. Nonetheless, the basic rule on thermal radiation still holds. As objects get hotter, they produce shorter wavelengths of light. So you can use this information to make your prediction as well. I should add here that by surface temperature, we're really describing the temperatures of the cloud tops. Most outer planets don't have solid surfaces, so cloud tops is usually the best we can do for a surface on these worlds. The equation that connects the peak wavelength of light to the temperature of the object producing that light is called Venns Law. This is given by T equals 2.9 times 10 to the 6th nanometers divided by lambda. T is the temperature, and lambda is the peak wavelength of light produced. 2.9 times 10 to the 6th nanometers is a constant, sort of like the gravitational constant we saw earlier. Like the gravitational constant, this one also tells us what units we need to be using for the wavelength, nanometers. Note that this equation gives us an answer in Kelvin. We don't usually write the kelvins in the constant for historical reasons. This is really a very simple equation. There is just one constant and one number we need to put into it, the peak wavelength of light emitted by each planet. So list those wavelengths for each of the planets you'll be calculating. Make sure you include the two that you predicted earlier. Notice that these values are already given in nanometers, so we don't need to do any unit conversions. You can leave that box blank. Let's go ahead and do this calculation. Simply replace lambda with the wavelength from the Mystery Solar System table and divide it from the constant to get the answer in kelvins. We'll do this calculation for a planet emitting light at a wavelength of 21,000 nanometers. As we divide them, we see that the answer is 138 kelvins. To get a sense of what that temperature actually means, remember that room temperature is about 300 kelvins. So 138 kelvins is incredibly cold, much colder than any place on Earth, but not an unreasonable temperature for an outer solar system planet. Now compare your answer to your prediction and decide if you've got it right. If so, say so here. If not, decide if the error is in the calculation or the prediction. If it's the prediction, explain what you should have predicted. One way to tell if the problem is with the calculation comes from looking at the values you're getting. Since you're working with outer solar system planets, the temperature should be a lot cooler than the Earth's surface. As we've already seen, room temperature is 300 Kelvin. So if you're getting temperatures much higher than 200 Kelvin, that probably means there's a problem with the calculations. Inner solar system planets can have hotter surfaces than this, but not outer. On the other hand, the temperature shouldn't be getting down less than 10 Kelvin, no matter how far from its star the planet is. So you should be suspicious of such low temperatures as well.